All right, let's consider some basic types of reactions. This is a very general view of these, and we're going to have some very general names on these as well. If you bring two elements or compounds together to make something new, you could call that synthesis or combination. If you take a compound and you break it into pieces, you would say it's a decomposition. If you take and you swap what is attached to something, so you would take, for example, this cation here, or this cation here, and we would change what is attached to it by taking B off and putting C on. We're going to call this single replacement. This is also a type of a redox reaction. And if you take and you swap what is attached to two of these, so you start with a compound and a second compound and then swap their attachment, we frequently call these double replacements. Now, examples on double replacements can be a precipitation, as well as an acid-base reaction. And we'll look at those in more detail in different sections. But for right now, we are going to focus on redox reactions. So the basic types that you need to know redox. Redox is a combination of two words, and that is reduction and oxidation. This is going to be a process where electrons are lost and gained. Sometimes it's not obvious that they are lost and gained, but nonetheless, best way to spot a redox reaction is if you have an element on one side of a chemical equation, and on the other side, and it could be either side, you have a compound, it is going to be a redox reaction. The second kind you need to know is precipitation. Precipitation reaction is when we make an insoluble ionic compound. So we're going to make an insoluble, and that means solid, ionic compound. So we're going to bring a couple things together to make an insoluble ionic compound, and that will be our precipitate, which we're going to shorthand as a PPT, and those are precipitation reactions. The last kind of reaction we're going to do are acids and bases, the simple of which is an acid-base neutralization, but we'll look at those in more depth in a different set of PowerPoints. Redox in action. Airbags. Airbags are filled frequently with sodium azide, and when sodium azide reacts, it goes into sodium and some nitrogen. We can balance our equation here. And when we balance our equation, we're going to get this. Note we have a compound on one side and elements on the other, and therefore it is redox. When this stuff breaks apart, it makes nitrogen as a gas, which fills our airbag. And this is one of the things they can use to make redox reactions, or one of these redox reactions that we can use to fill airbags. This is a view of a precipitation reaction. If we take lead and we let it mix with some iodides, we're going to make a solid ionic compound. That is the yellow stuff in the bottom of the container, and it's going to be lead iodide, and it's going to be a solid. And this solid is going to be our precipitate. Here, shorthand is a PPT. When we do this, and I note it's a solid, it's frequently a powdery solid. It's not a rock. That's geology. That takes time and pressure. This is just going to be a little bits of a solid in the bottom of a container. So let's start with redox. The obvious redox reactions are electron transfer reactions, and we're going to have two parts to these. We're going to have something that is losing electrons and something that is gaining electrons. Now, if we have an ionic compound, this becomes fairly obvious. Our magnesium here at the front is neutral. This means it's got 12 protons and 12 electrons, and it's going to go into magnesium 2 plus. Magnesium 2 plus still has 12 protons, but now it only has 10 electrons. So in order to go from magnesium to magnesium 2 plus, it is going to lose electrons. When we lose electrons, we say it has been oxidized. And the loss of electrons will be our oxidation half reaction. Now, reduction is not a chemical term, it's actually a meteorological term, and it is going to be gain of electrons. Now, oxygen is gaining. Oxygen here, each oxygen atom has 8 protons and 8 electrons, and it's going to go into oxygen 2 minus. When it does that, it's going to have 8 protons and 10 electrons, which means it's going to gain 2. And when it gains 2 electrons, it is going to be reduced, and that is going to be the reduction half. Now, when we do these in real life, the number of electrons lost has to equal the number of electrons gained, and that is a trick that we're going to use or can use to balance reactions. So here we have a solution where we have silver plus ions in and some copper wire, and we put the copper wire inside the silver, and we get a reaction. Over here, we're going to see some blue solution. That's actually copper 2 plus. That's making that nice blue solution. And there's going to be a gray kind of silvery on there. And that is because the silver has become electroplated. It's actually stuck as a metal onto the piece of copper wire. And this is what's happening. Copper is losing electrons to make copper 2 plus, and that copper 2 plus is going into solution. The silver is going to gain those electrons. It's going to gain them right on the top of the copper where the copper is losing and making Ag plus. Now this is displacing the copper on this displacing the copper on this piece of copper wire. And we're going to get a nice redox reaction. Silver is being reduced, copper is being oxidized. So let's consider the sodium and the chloride. In order to do this, we're going to realize that we're coming from a neutral species, sodium and chlorine, and it's going into some ions, sodium plus and chloride minus. And in order to do this, our sodium is going to lose electrons, which means sodium is being oxidized. Chlorine is going to gain electrons, which means chlorine is being reduced. And the combination together is going to be redox. Now, there's other terminology that we use. Sodium, which is being oxidized, so sodium is losing electrons. And we say that it is a reducing agent, means it provides electrons or causes chlorine. Chlorine is gaining electrons. By gaining electrons, it is removing electrons or oxidizes sodium. So whatever is being reduced, so chlorine being reduced, is the oxidizing agent, causing the other one. Therefore, sodium, which is being oxidized, is the reducing agent. Now, we can also say oxidant and reductant, but mostly we say oxidizing and reducing agent. Some redox reactions, and note this is elements going into a compound, do not obviously involve the transfer of electrons, and that is because these are all nonmetals. Now, we can still view them in terms of a transfer of electrons, and instead of looking at them in terms of electrons lost and gained, we're going to kind of look at a pretend charge on these guys, and our pretend charge is going to be an oxidation number or an oxidation state, which would be the charge if the compound itself were ionic. So if HCl were ionic, the H would be a positive 1 and the chloride will be a minus 1, and we would say that the hydrogen is being oxidized and the chlorine is being reduced. Now, those are not real charges. That's not an ionic compound. So these are pretend charges, and we're going to assign these pretend charges and call them oxidation numbers or oxidation states. So let's look at some rules. So oxidation state, if we have any element, the oxidation state is 0. So if we have sodium or chlorine or S8, it doesn't matter. These are elements and their oxidation state is 0. And we frequently write the oxidation state as a subscript to the right. The oxidation state on any monatomic ion is the charge. So if I have CaO, I know that this is an ionic compound, and calcium is 2 plus, and oxide is 2 minus. The oxidation state of an ion is its charge. Now, quick note, our oxidation states are going to add to 0. So the oxidation states add to 0 for a compound, and they add to the charge for an ion. Okay, we'll do that in a moment. Now, there's a couple else that matter, and really not many after that. If we have hydrogen with a nonmetal, it is always going to be +1, and hydrogen with a metal is -1. That also comes out of rule 2 with the monatomic ions. And oxidation, the oxidation state of oxygen is almost always -2 unless it's a peroxide. And we'll do examples on all of those. And that's really all you need to know. Elements are 0, monatomic ions are the charge, hydrogen with a nonmetal is +1, hydrogen with a metal is -1, oxygen is almost -2. And then they add up to either 0 for a compound or to the charge for an ion. So let's do some examples. If we have ammonia, we're going to stop and look at this and realize that hydrogen is with a nonmetal. So hydrogen with nonmetal. Anytime hydrogen is with a nonmetal, it's going to be +1. So each hydrogen is +1. Because each hydrogen is +1, and there are 3 of them, this is a total of +3. Now, the oxidation numbers add to 0 for a molecule, which means this has to add to 0, because this is a molecule. Therefore, there's 1 nitrogen, and it has to be -3. So we say the oxidation state on hydrogen is +1, and the oxidation state on nitrogen is -3. Do another one. If we do another one and we say we have ClO2 minus. All right. Oxygen here is going to be -2. And there's 2 of them. So that's going to be -4. Now this is an ionic compound, so it's going to add to the charge, and that's -1. We have 1 chlorine, therefore it has to be +3. +3 -4 is equal to -1. And we say the oxidation state on chlorine is +3, and the oxidation state on oxygen is -2. So +3 and -2. We can have some more interesting ones because we can have things like KMNO4. KMNO4, potassium is an ion, it's +1. Oxygen is -2 each, and there's 4 of them, so that's -8, and that's +1. Because this is a compound and there's no charge here, that's going to add to 0, meaning the manganese has to be +7. That's it. Those are oxidation numbers and oxidation states, and we are going to take and use those, or can use those, for balancing reactions. So redox reactions are a combination of oxidation and reduction. When we have oxidation, we have an increase in oxidation number. So what might that mean? Well, if aluminum is being oxidized and it's going from Al into Al3+, and it's going to lose 3 electrons, we know oxidation is also lost. Our oxidation number goes from 0 to +3, and that is an increase. Reduction is a decrease in oxidation number. So if we have copper 2+ gaining 2 electrons to go into copper, its oxidation number is going from +2 to 0, and therefore it's reducing. It's going to decrease in the oxidation number. So a couple of types of redox reactions. We've already talked about single displacement or single replacement, and we can look at these and see that this is one thing is being replaced. We're replacing the silver with the copper, hence single replacement. Now this is also redox, and we know this is redox because the oxidation number on an element is 0, so those 2 are 0. Nitrate has a -1, therefore silver is +1. Copper is with 2 nitrates, therefore it is +2. We know that copper is going from 0 to +2, so it's being reduced. Excuse me, it is being oxidized. Silver is going from +1 to 0, therefore it's being reduced. And that is a single replacement or single displacement reaction where copper is being oxidized and our silver is being reduced. All right, combustion reactions. Now we've seen combustion reactions, and combustion reactions could be as simple as the methane that's in your heater or in your gas stove reacting with oxygen to make carbon dioxide and water. And combustion reactions occur when we have redox and we make lots of heat. Frequently we get a flame as well. In this case, though, this is a redox. This is also a combustion reaction producing lots of heat and sometimes significant amounts of light as well. But in this case, if we take a look at it, we realize that aluminum is starting at 0. It's making an ionic compound, so it has to be +3. We know that the nitrogen is changing oxidation numbers, and we know that because it's element over here, which means it's got an oxidation number of 0. If we did the separate pieces over here, its oxidation number would change. And the other interesting one is that the chlorine's oxidation number is changing. So this is one big redox reaction. Lots of things are changing oxidation number.